Mr. Doug Mouton and Mr. Byron Best. Welcome to Let's Talk Tech. Thank you for joining us today to talk to us about Fidelis New Energy.
Thank you for having us. My name is Doug Mouton. I'm very excited to be part of the Fidelis team, where we are looking for ways to help transition the energy economy from fossil fuel into hydrogen and other renewable pathways. The application for the technology that Fidelis is generating is wide and reaching. It can help many industries like the data center industry, manufacturing, as well as provide a great source of carbon credits for industries looking to offset their carbon loads.
So we work in a couple different verticals. So we do sustainable fuels, so things like renewable diesel and sustainable aviation fuel. Actually is immediately relevant. Almost everyone I've talked to at the conference uses what they call HVO, which is basically renewable diesel to supply emergency backup power to data centers. So we have a project in Baton Rouge, Louisiana called Project Grow, which can supply that same fuel to these types of facilities. Then we have low carbon hydrogen. So we have a technology that we call Fidelis H2 to make zero carbon hydrogen from natural gas at scale using only proven technologies. And that's actually directly applicable to the data center space, because we view that as a great opportunity to make zero carbon dispatchable power to effectively decarbonize data center operations directly. We also offer carbon capture storage as a service. So we do that with our Norn Carbon Storage Hub in Denmark. And then finally, as Doug mentioned, we offer a CDR sales business. We have approximately over 1 million tons per year of projects in the pipeline. The first one being called our Atmosphere project in Baton Rouge, Louisiana.
The energy transition period and what's happening in the decarbonization phase.
I think for the data center industry specifically, we're at this intersection of growth, and we're reaching the capacity of land and power availability to support the growth of compute and AI services that the industry so desperately needs. And what we're able to do at Fidelis is create a pathway to hydrogen with gas turbine technology that can give power to our data centers now to create what's called island power. But we're taking the carbon out before we generate the power, and we're able to sequester that carbon, giving our clients a carbon neutral power source for their immediate needs as the technology catches up to perfect at scale hydrogen for our sites.
Decarbonizing the construction of data centers, reducing scope 3. Explain to us about scope 1, 2, and 3.
Scope 1 emissions are actual CO2 that's emitted to atmosphere in the course of a business's operations. So they were burning a fuel that contained carbon, and then that's emitted to atmosphere directly. Scope 2 emissions are associated with power or heat consumed at a site. So that's carbon emissions embedded in electricity consumed from the grid, natural gas, etc. Then scope 3 emissions are embedded a couple of different ways that they come in, but they're basically embodied emissions, mostly in goods or services that are consumed by a business. So you utilize a product during construction, your employees travel to and from a site. All of those emissions add up to scope 3 emissions.
So the embodied carbon is very spread out. It will be in all the materials, building materials, equipment, computers, everything. And that's hence the difficulty. Hence, whenever I mention scope 3, everybody's going, no, that's too complicated. We're not dealing with this.
Right.
How are you helping?
Well, we're trying to simplify the problem. And the way I'd like to start is follow the money. Where is the money spent to create a data center function? And we see it in the actual construction of the building, just like Byron mentioned, the goods and services, the waste generated, the transportation, and also what goes into that data center, the servers themselves. So we see a tremendous amount of scope 3 emissions or embodied carbon in the equipment, the mechanical electrical equipment that makes up half of the construction cost and half of the emissions in scope 3 terms for the data center building itself. Then we see the building envelope, the structure itself. And it's a combination of concrete and steel for the most part that makes up the second big chunk of emissions for scope 3. And then that's followed by, believe it or not, diesel emissions when we do all the earthwork involved to create these large buildings that create the need for us to scrape the land and shape the land. And those emissions can count up to 10% of the emissions for the building itself. Now, when we fill up that building with servers, there is a tremendous amount of Scope 3 emissions involved with the servers, almost as much as involved with the first building itself. And because the building's life cycle lasts so much longer than the life of the server, we will see the lifespan of servers last 2 or 3 times within the data center life, meaning that we will turn server populations. So when we look backwards at all the Scope 3 emissions, the servers will be by far the biggest source of Scope 3 emissions. Now that is a topic that we all need to work on together as an industry. However, when we think about people that make data centers, both the hyperscalers and the colo providers, it's something we can all focus on together, and that is the buildings themselves and understanding where that carbon is and doing a number of things that we can get into to help reduce that.
Scope 1 emissions, well, first of all, for hyperscalers, it's really not that significant of an issue. It's mostly coming from diesel backup power, and it's a relatively small fraction, like a single-digit percentage of their total carbon footprint. Scope 2 is a complex issue that has a lot of moving parts. A lot of it kind of comes down to semantics. If you look among the 5 largest hyperscalers, 3 are already near zero Scope 2 emissions in their own, using their own sustainability criteria. And they're achieving that by purchasing things like RECs to offset carbon intensity of consumed power, or using PPAs to reduce the carbon intensity of the power that they're consuming. The Scope 3 emissions are a lot more complex, because you can imagine, even if you just have a single data center, you have one Scope 1 emissions point. If you wanted to, you could add carbon capture to it. You can use a biofuel. It's relatively easy to mitigate. With Scope 2, you have one point of power inlet, like one grid connection, and decarbonizing that using a contract is also relatively straightforward. But like Doug was saying, when you look at the number of different materials that you're consuming during the construction process and what's necessary to make the data center work in terms of IT equipment, that's coming from a very large number of different suppliers, all of which have their own carbon footprint. And trying to eliminate those Scope 3 emissions, that's something that we all want to do, but it's just not practical to get that to zero. So in order to deal with that residual Scope 3, we sell CDRs, so carbon dioxide removal credits, which are basically an opportunity to clean up those emissions. And rather than having to go to like 10,000 different points to eliminate the carbon emission, basically we can sell carbon dioxide removal certificates to say, hey, we may have consumed this Scope 3, but we're also carbon negative. We're taking this carbon out of the atmosphere, and thus we can achieve carbon neutrality using this pathway.
And if you can think of a path or a mechanism to make that happen.
I believe that the hyperscale data center industry is in a position to really lead the way and show other industries how to do this. And I'm excited by what's already happening. And that is the big consumers of this mechanical, electrical gear that heat and that cool and power our data centers. It's a finite group of industry players that, like you said, they show up at these conferences and the buyers show up at the conferences. And the first thing we've done is we've all agreed that we should measure and cause to disclose our supply chain for them to tell us everything that's inside from a carbon perspective in the products that we buy. Environmental product disclosures. Large movement has happened across the iMasons, where all the hyperscalers and major colo providers, even major suppliers like Schneider Electric, have signed off on this commitment to first disclose what carbon is in these pieces of equipment that we buy. And then the next step is, if we can measure it, we can manage it. And then which providers can then show a differentiation of their products to this market, which is marching towards $1 trillion market, to provide goods and services that do meet our aspirations to lower their carbon.
Where are the regulators? Where is the government in all this? Is there a conversation being had with them, or do you expect that the industry will self-regulate?
What's happening now, it's a self-regulation process. And I suspect as we look globally, Europe seems to be the bellwether for more environmentally forward regulation and intervention. And we hear that the SEC in the US will start to require companies to disclose emissions.
The voluntary market and then the hyperscalers staying true to commitments is the key driver right now. Google committed to and then became 100% offsetting of their Scope 2 emissions by 2017. Microsoft is targeting to become carbon negative by 2030 and then to offset all of their historical emissions by 2050. So clearly government regulation will help, and both a carrot and a stick approach. So like an ETS penalty here in Europe, the incentives of the Inflation Reduction Act in the United States. But coming over the top of that, companies like Microsoft and Google stepping up and paying a premium to have lower carbon service is ultimately going to drive a major change within the market.
And is there any observer to check that what they're pledging or claiming is correct?
Years ago, when power was first showing up as something that should be measured, Greenpeace gave all the hyperscalers, including Apple, a grade based upon the quality of their power.
Okay.
And it was not pretty. When these large technology companies got graded by Greenpeace, it created a watershed moment in the industry where suddenly renewable power was extremely important to the C-suite of these companies, and hence what Byron's talking about, these PPA agreements. And we see largely a lot of the, in fact all of the large tech companies are on a pathway, if not already at net zero for Scope 2 emissions through offsets. Well, the second one was the invention of the PUE by Christian Bellotti, who said there's going to be a common way to measure efficiencies in data centers relative to how much of the power utilized by the data center is for cooling versus for running IT loads. And when those metrics started to show up, it became a way for industry to compare itself to each other relative to how efficient they were with their designs. And that was probably the next movement that helped drive down consumption.
So can you tell us about the impact of AI on the effort that you're trying to do?
It turns the plans on its head. The large corporations in tech have committed to sustainability goals years ago, probably 3 years ago, with very ambitious goals to 2030, just like Byron said, to get not only to net zero, but to make up all the past emissions as well. And the cloud business was already showing a strong growth that was accounted for when these plans were made. But AI sits on top of that growth projection and just turns the plan on its head. And it makes this even bigger pressure point for us to get faster and better at lowering the carbon.
Is the 2030 a pipe dream with AI? Are we going to have to readjust the targets?
Metrics need to evolve. I think in terms of thinking about total carbon, it's pretty unrealistic thing you could add all this growth and still hit a zero number at a fixed date. But I think to really measure progress, just like PUE showed up as a way to measure relative performance, I suspect we should all be thinking about what is our cost per unit delivered, what is our carbon content per unit delivered in terms of scopes of emissions, so that we can all be marching towards zero in a way that we can measure our progress along the way.
What is a realistic timeline now?
I wouldn't change the timeline because it's good to be aggressive. Like
I think you're right.
An enormous change in approach in order to meet the goal.
Yeah.
And I think keeping 2030 is the right thing to do.
I mean, what is your assessments, having looked at all sort of climate tech available?
Before liquid cooling came into play, the hyperscalers were using a method called adiabatic cooling, simply manipulating humidity and air movement and creating some very efficient first cost systems and very efficient life cycle cost systems. No longer can we depend upon that. We have to use these liquid cooled systems. Do we know the full impact? Not yet. I think we will be able to do things we couldn't do when we were an air-cooled world. We can make these buildings more compact. We can drive, efficient cooling to the chip in a way we probably don't even know yet in terms of what kind of efficiencies we can drive. In fact, we saw some presentations today that argue we can even improve our PUEs with liquid to the chip. So I'm hopeful that we can realize that. I'm worried about the carbon intensity of the mechanical equipment that is needed to create the cooled water and to cycle it through. Folks that are using seawater or other sources of thermal grounding may be some of the solutions that could help us get to a really low energy.
In certain areas where there's a need for district heating, it actually probably makes that process easier, like collecting the heat and getting it into a transfer heating.
How to design AI data centers without wrecking the environment.
The current construct, as we consider what these large language models need from a built environment, we're making a collection of servers that are connected with fiber optics, much like a brain. And it wants to be on the same level, it wants to be in the same building. And when we extrapolate, what a 1 million GPU large language model looks like, it starts to become a 500,000 square foot building very quickly. And when we start to look at the impact of moving the earth around and shaping the ground, just when we clear and grub the ground, we take out a lot of beautiful plant life that's doing its job, absorbing carbon dioxide and creating oxygen, and that's been released to the environment. Then we have to emit all the diesel fumes to do the movement of the earth itself. And then we create these large buildings that are largely there because of a technological constraint that we believe that the fiber optic connectivity between all of these servers must be so close. The latency must be small. I'm hopeful that technology will enable a more decentralized capability for training models so that we can create more efficient space.
Do you have any comment on hyperscaler practices?
One of the things that the business gets criticized around is we're buying PPAs for our Scope 2 emissions. And we just saw a presentation today that says, okay, you can buy all the PPAs you want, but Poland still has this much dirty power. The US still has this much dirty power. And that's what's fueling our data centers. I'm curious if we're sequestering or pulling off the carbon in a gas turbine delivery, can we then feel good that we have created a low carbon energy for Scope 2 emissions at the source of use versus buying it through offsets or PPAs?
Yeah, I think there's a fundamental challenge in that renewable generation, if we're talking about solar and wind, is intermittent, and data centers want dispatchable power, right? Like they probably run at an average capacity factor of 60%, give or take, and it's pretty flat. So building renewable generation without energy storage to meet that demand probably exacerbates grid instability. So I think this gets very complex and has to do with how they're structuring their PPAs in order to make sure that they're encouraging renewable build out, which is good, but at the same time trying to incentivize doing it in a sustainable way that supports good grid function. So basically making sure that where necessary, either gas peaking plants are coming to help stabilize power production as renewables fluctuate, or using demand response in the data center. That was something that we heard at the conference in order to try to support almost as a grid ancillary service.
We are sequestering or pulling off the carbon before we're generating the power, and it's at the point of use.
There you go. The last option would be building more low carbon dispatchable power. So clearly having carbon capture and sequestration embedded in power generation, either through post-combustion capture on a natural gas combined cycle turbine or firing hydrogen that is zero carbon in the first place would be a really good solution.
Okay, I have another question for you. It's kind of crazy. I've been thinking about this. All these gas turbines, assuming we can pull the carbon dioxide off of them, we also have an opportunity with enough gas turbine production to get heat absorption, if I'm not mistaken. We can create a cooling loop. And could we use carbon dioxide itself as a refrigerant in a compressed state and not only have, but not district cooling, but district cooling for these data centers to drop their heat off as a byproduct of this methodology you're thinking about?
There's definitely a concept called trigeneration, which is being explored, which is where we have, so a simple cycle gas turbine just is basically the same engine you would have on a plane. And combined cycle, we're taking the waste heat from the exhaust, we're making steam, and then putting that through a separate cycle to extract more energy. Trigeneration, we then take some of that steam that we produce, and instead of making power, we send that to an absorption chiller, and then we can provide chilling to the data center as well. So I think that's definitely something that's going to be practiced and an opportunity for optimization that I think is really exciting for the industry.
The Fidelis carbon neutral power plant with path to hydrogen, which I believe you have in Denmark.
West Virginia is where we have the first site that we think is a candidate. We don't know that we have scale yet in Denmark for this.
So our Monarch Cloud campus is a future zero carbon data center complex in West Virginia. We have 2,200 acres, and we have enough natural gas to power about 2 gigawatts of hyperscale campus. So the strategy is speed to market and power availability is a huge constraint, particularly in the PJM interconnect. So because we're starting from natural gas behind the meter, we have the opportunity to scale very rapidly with probably 400 to 500 megawatts within about 24 to 30 months. So we also have the opportunity using our Fidelis H2 technology, where we can make zero carbon hydrogen from natural gas, to design and install turbines that can run either natural gas or hydrogen. So there's flexibility, and when the end user wants to decarbonize, we can feed hydrogen into those turbines to decarbonize the operation. Atmosclear is a CDR generating facility to be located in Baton Rouge, Louisiana. Basically, it's a biomass energy with carbon capture and sequestration plant, or a BECCS plant. So the concept is that the biomass is a waste, but it's sustainably extracted CO2 using photosynthesis from the atmosphere. So we combust that biomass to make energy. We take the flue gas and then send that to a post-combustion capture unit, and then that ends up being sequestered in a geologic formation that we have under control at the Sherburne Wildlife Management Area. So the net effect is you're taking about 620,000 metric tons per year of CO2 that's being removed from the atmosphere and then sent to sequestration. So it's effectively a carbon negative process. So we then sell CDR certificates to hyperscalers looking to decarbonize, especially with like scope 3 emission.
If you had the chance to evaluate some of the efforts happening in different parts of the world.
What's new to the carbon capture and sequestration market is this huge drive coming from hyperscalers to decarbonize. So historically, there's been several successful projects in the United States. We have Petronova in Texas, we have SaskPower Boundary Dam in Canada, but the economics of those facilities to operate were driven by enhanced oil recovery. So for example, with Petronova, when oil prices crashed, there no longer was that incentive and it temporarily paused operations. What we're seeing is that hyperscalers want to decarbonize very aggressively, which provides that larger economic incentive to ensure continued operations. So the technology works. There just needs to be that economic incentive to push people to carry it forward and be sure and make sure that those tons of CO2 are being stored underground. This is a new drive that we're seeing that's getting even stronger with the growth of AI. So I think we're going to see many more tons of CO2 successfully sequestered in the future.
I'm curious about the cost per ton sequestered, and I really want to learn more about other ways we can naturally sequester carbon, like through promoting restoration of forest land or regenerative agriculture. Stuff that really allows our botany to come back into full force. And I don't know that it will scale that well, Byron, but I'm just curious about the cost of it, and it'd be a great thread to pull.
What we're kind of touching on is the difference between like carbon offsets and engineered carbon removals. So offsets are available in the current market. They're relatively inexpensive. I think a lot of that has to do with some failures in the history of that market, where things like protecting from deforestation ultimately was not successful, which created some doubt and suppressed some trust issues. On the engineered market side, there's really two pathways. One is called DAC, or direct air capture, where I basically have a giant fan that pulls air in. The atmosphere is currently about 450 ppm CO2, so it's quite dilute, but you concentrate that and then send that CO2 to sequestration. The other approach is what we were talking about earlier, like the Atmosclear project, BECCS. From my perspective, BECCS is more immediately scalable at the economic price point that we need. I think DAC is definitely interesting, but probably will take us out in the 2030 and beyond timeframe in order to get to the billion plus ton per year scale that we need to help hyperscalers meet their decarbonization goals.
If we were to meet here again in a year's time, do you imagine that the needle would have shifted on this conversation?
I would be so excited to see some tri-generation going on at Project Monarch, with district cooling and hyperscalers coming in and really pushing the envelope with some thoughtful scope 3 emissions approaches to designs and more collaboration amongst the equipment suppliers to really double down on how they can help us lower the carbon footprints.
Optimistic that we'll see dispatchable behind the meter low carbon power generation like at our Monarch Cloud campus. I think that that'll be really key to support hyperscaler goals with the rise of AI, but doing it in a sustainable way. I also think that we'll see continued growth and traction in the CDR market. That is going to be vital to offset Scope 3 emissions. And I think we'll see a lot of announcements in the next year as to the projects reaching FID and helping hyperscalers meet their goals.
Doug and Byron, thank you very much. We're very privileged to be joined by these two experts all the way from Texas here in Antibes, and we look forward to welcome you again on Let's Talk Tech.
Thanks for having us.